And then to determine what happens at each x-intercept, we look at the multiplicity, right? So this is minus 3 to the third. So that means that function is going to come down and flatten and go through. Right? At minus 1, it's a squared, so it's going to touch and come back down. And at 3, it's a 6, so it's another even power. It's going to touch and come back down. Right? And so that's the rough shape of the graph. Right? And that's the information you should have gathered, right, from doing this by hand. Are there any questions about that problem? Okay. Here's one other I wanted to show everybody. So your goal is to find all the zeros of this function. Start with the potential rational zeros. So the potential rational zeros, I take the factor of 10 over the factors of 1. So it's going to be plus or minus 1 over 1, 2 over 1, 5 over 1, and 10 over 1. So the only possible rational zeros are going to be these values. What we do here is we just start testing, and you can do this, you know, show each one, but we can see that 1 and minus 1 are never going to be 0 because of this minus 10 here. But it turns out f of 2 is 0, right? That's 8 plus 4, that's 12, minus 2, minus 10, minus 12. So this is the key idea. Once I know that I have a factor, x minus 2 is a factor, then I can do long division or synthetic division. Right here are the coefficients. I do my division and I get a remainder of 0. And what that tells me when I do the division is that this original polynomial, x minus 2, divides into that evenly. Right? So this original polynomial here actually can be rewritten as this. I have one of the zeros. I know there are 3 zeros because it's degree 3. And so the other 2 zeros, I'd factor this if I could. But since I can't, I use the quadratic formula and I get these 2 imaginary zeros. Right? These are conjugate pairs, and we're not surprised about that because imaginary zeros come in pairs. Right? So those 3 zeros are here. Okay. So this problem is kind of putting those ideas together about imaginary and real zeros and rational zeros and how we can break down polynomials using that information. Okay, so that's an important type of question to make sure we know how to do. Okay. All right. So again, I'll have, like I said before, I'll have those midterms done by tomorrow. You know, it's taking me a little bit longer. I have a couple issues, a couple students' exams that I have to look into in more detail, unfortunately. But for everybody else, we'll get those done. Get those done soon. And I apologize. It should have been done a little earlier, but sometimes that happens. Okay. Are there questions from the homework at all? Any questions from the homework we should look at?
What's and well, like I can't even say like what is it asymptote or whatever.
Yeah, it's a terrible word, right? Asymptote. You kind of skip the P, I guess, or asymptote.
Okay.
Yeah. Yeah, okay. Let's talk about that. I mean, let's kind of introduce the idea that we're working on here in chapter 4. There are some similarities between chapter 4 and chapter 3. Chapter 3 was focused on polynomials, and we learned some things about zeros and x-intercepts. And that information still holds true with rational functions and other types of functions too. But rational functions have this extra feature, this asymptote feature. So remember, a rational function, could look something like x plus 2 over x squared minus 9, right? The rational means fraction. And so we have some kind of different properties than we do with polynomials. But in the same way, we want to try and figure out some of these properties and be able to identify them from looking at the function, right? So like the last example I just did, right? We use that to find the x-intercepts, or the graphing example that I did. We're trying to analyze this function the same way. And so I'd say just the easiest things to start with are the intercepts. Whatever function you're working with, the intercepts are almost always a good place to start. They are important points on any function. The y-intercept is the easiest here, because the y-intercept is just f of 0, right? Anytime you have a y-intercept, you just set x equal to 0. And in this case, then you get 2 over minus 9, right? Or minus 2/9. The x-intercept is where 0 equals, right? The output is 0. And one of the nice things about rational functions is that the only way you have a fraction that's equal to 0 is if the top is 0. If the bottom is 0, then the thing is undefined, right? And it doesn't matter what number the bottom is, as long as it's not 0. If the top is 0, right? 0 over anything except 0 is going to be 0. So this only happens when the top is 0, which is at x equals minus 2. So when we're looking at a rational function, the y-intercept, we don't know. I mean, we just have to analyze it and put in x equals 0 and see what happens. But the x-intercept is where the numerator equals 0. So anytime you're working with this, you set the top equal to 0. That's going to give you the x-intercept. Okay. Let's talk about the denominator now. So where the denominator equals 0 is going to make this expression undefined, right? I can't evaluate it when the bottom is 0 because it's undefined. So that the function doesn't exist there. But what's happening is, as the numbers get really close to 0 in the bottom, that makes the expression go to infinity, right? This is a really large value then. And so what this does for the graph is this creates what's called a vertical asymptote. So when the denominator equals 0 and the numerator does not equal 0, so that's important. We'll talk about what happens when they're both 0. But if the denominator is 0 and the numerator is not 0, that's going to be what's called a vertical asymptote. And what that looks like on the graph is, as I approach that value, as the x values get closer and closer and closer to whatever is making the denominator 0, the function is going to go either to positive infinity or negative infinity. So it's going to go one of those two directions, and we'll be able to figure out which way it goes. But I know it's going to blow up, right? That's what really a vertical asymptote is. It's where the function is blowing up. And it's, again, it's probably easiest to see that numerically. We can see here around 3. 3 is making this number 0, so it doesn't exist there. But as we get close to 3, it needs to make that value when I divide that, it'll make the value very, very large. I'm sorry, I have to pause for a second. Okay, so sorry about that. So we identify the vertical asymptotes by looking at where the denominator is equal to 0. And so in this case, that's going to be where x squared minus 9 equals 0, right? X plus 3, x minus 3 equals 0. So x equals 3 and minus 3. At those two values, I'm going to have a vertical asymptote, which means the function is going to blow up at that value. And again, we don't know yet which way it blows up, right? Each side is kind of independent of each other. So let's take a look at the information we have so far and try and come up with a rough sketch of what's happening with this function. So I have a y-intercept of minus 2/9, which is, you know, somewhere in there. I have an x-intercept of minus 2, which is somewhere there. And then I have these vertical asymptotes at 3 and minus 3. And the way we indicate vertical asymptotes are with these dashed lines. So the function isn't actually on that dashed line. That's just like a guide to help us figure out what's going on with the function. Now, I don't know yet kind of how the function is behaving. I have some information, but I don't know yet what's happening with it. And so what would be really helpful would be to figure out the end behavior. So we know for polynomials that each end either goes up or it goes down, right? And we can figure that out. We had a rule for that, right? We saw that in the example that I did. If the power is even, right, they both go up, or one's up and one's down. Rational expressions are different. So rational expressions, we have, as x gets larger and larger, we have both a numerator and a denominator. So what happens here is we have to compare the two, the numerator and the denominator. So let me copy this over and we'll talk about horizontal asymptotes, and then we'll come back to this question and see if we can't complete the graph. So I have f of x equals x plus 2 over x squared minus 9. And so end behavior is really like what happens as the x values get really large, either positive or really large negative. And to do that, I'm going to compare the top and the bottom. In this case, if the degree of the denominator is larger than the degree of the numerator, that's what I have here, right? An x squared on the bottom and just an x on the top. What that means is the bottom is getting a lot bigger. As x is 100, 100 squared is a lot bigger than 102. And 1,000 squared is a lot bigger than 1,002. It gets bigger and bigger and bigger on the bottom, not nearly as fast on the top. This implies that y equals 0 is what's called the horizontal asymptote. So the horizontal asymptote is really like is really like end behavior for a rational function, right? Does it approach some particular value, or does it do different things? So y equals 0 is a horizontal asymptote in this case. If you have 2x squared plus 3 over x squared minus 5x plus 2, this is your function, call it g of x. We again want to compare the degrees, and what you can see is that the degrees here are equal between the top and the bottom. If the degree is equal, y is going to equal, in this case, 2 over 1, which is the ratio of the leading coefficients. Okay.
Could you go over that part one more time, like why it's leading coefficients?
Yeah.
I don't know. It's kind of confusing me a little bit. I don't.
No, you're right. It's kind of a different idea. What happens is, what's really happening here is like, I'm claiming that 2 is the horizontal asymptote, and what that means is as the x values get larger and larger and larger, the function is going to be getting closer and closer and closer to 2. So it may go kind of up and down, or it may just go kind of like this. It's going to get closer and closer to 2. And if we imagine, again, this numerically, like as x is 100, the adding 3 and subtracting 500 plus 2 is not changing it very much, because 100 squared is quite big, right? That's 10,000. So this is really, the top is like 20,000 and the bottom is like 10,000, you know, off by just a little bit. And so that ratio is pretty close to 2. Right? And as x gets bigger and bigger and bigger, these values here get even less significant, right? When x is a million squared is, I don't know, a lot, and adding 3 to it is inconsequential, really, right? So that ratio gets closer and closer to whatever these leading coefficients are, so 2 over 1. Right? I can ignore all of the rest of that stuff. And you know, again, that can happen in different ways, but in the end, it's going to get very, very close to 2. Was that
That kind of made sense.
What you were looking for?
Kind of made sense.
So at this situation, what we really pay attention to is the powers, right? Or the powers.
Yeah, when the degree is equal, like this, x squared over x squared or x cubed over x cubed, then you just look at the numbers in front, the leading coefficients. That turns out to be the only thing that really matters for the horizontal asymptotes. If you know, you could try like actually sort of plugging in some numbers, some x values here, and seeing how that ratio is going to get closer and closer to 2 as the numbers get bigger and bigger and bigger. This is another example. What if I have f of x equals 3x to the 5th plus x to the 4th minus 2 all over 4x to the 5th minus 17. This is the same situation for the horizontal asymptote. These are both degree 5, so I can just focus on that ratio. This line, y equals 3/4, then is the horizontal asymptote. I'll often write the horizontal asymptote just like that, because like we said, asymptote is a unpleasant word, right? So you can save yourself a little grief. I will remind you that the book once asymptotes written as lines, asymptotes are lines. So you can't just say 3/4. You have to write y equals 3/4 because that's what the horizontal asymptote is. If you've done the homework, you've discovered that. But if you haven't yet, then that will help you. Okay.
Can you draw that graph of that asymptote?
Sorry, say it again.
Can you, the 3/4, can you draw the graph of that one?
Yeah, so it's just going to be a line. Like the horizontal asymptote is, all that tells me is that there's a line at 3/4. So y equals 3/4 would be, you know, that line just below 1. Now, I don't know, from that information, I don't know exactly how the function will approach that line. So this function is actually pretty complicated. I don't actually have a good sense of what it's doing. Functions can cross over this line, they can stay above it or stay below it. I'd have to look at other things to figure out what's going on there. All I know is that in the end, it's going to be getting close to this value 3/4. Could be looking like that or like that. Okay. So it's not, the function is not going to go down like this. Right? I know it's heading towards 3/4 eventually. But again, all the stuff in here, it could be doing lots of other things in here. And then, you know, in the end, heading towards 3/4.
Okay.
Okay. So think of, we call it horizontal asymptote because of the way it's getting close to that value, but it's really like just end behavior. It's describing like what's happening out on the ends of a rational function. Other questions? These are excellent questions. Okay, there's sort of two other cases here. So in this case, the numerator is larger by 1, right? X squared and x. So if the numerator equals denominator plus 1, that's going to be what's called an oblique asymptote. And I don't necessarily, this is kind of like 4.2 stuff. So I'm going to wait to kind of talk about how we find that. But an oblique means like on an angle. So horizontal asymptote is a straight line, oblique would be on an angle. So it turns out if the degree is 1 larger on top than on bottom, then you get an asymptote that's a line, an angled line. So, you know, your function might look something like this. It's getting closer and closer to that line. If the numerator is bigger than the denominator, plus 1, no asymptote. Ran out of room. No asymptote. So it's a little tricky to talk about here because these are called horizontal asymptotes. Y equals 0, y equals 2, y equals 3/4. Those are horizontal asymptotes. This is called an oblique asymptote, but it's like a horizontal asymptote. I mean, it's not horizontal, but all of these are possibilities. You can't have an oblique asymptote and a horizontal asymptote. You can possibly have an oblique or horizontal or no asymptote. Okay, so those are your options for this horizontal asymptote question. Okay, so we'll talk about how to find this later, but that is a sort of third option. Okay. it's again a way of describing the end behavior. So let's go back in time here. This was our original problem. The denominator is larger than the numerator, so this is a horizontal asymptote. So I know that eventually the function is approaching y equals 0. Okay. So the final question here is to say, can I put this together now to figure out what the graph looks like? Now, each of these individual components are questions that you will be asked. So I might just give you a function and say, what is the x-intercept, right? And you say -2. Or I might say, what are the vertical asymptotes, right? And you do this. Or what's the horizontal asymptote? So all of these questions will be asked individually, and that will be important. But we also want to be able to take that information and come up with a graph. Now, there are some things that we can figure out here. We don't know exactly what the graph looks like, but I do have some information. One piece of information I have is that the only x-intercept is at -2. So the graph cannot cross the x-axis anywhere else because that would be an x-intercept. I also have this y-intercept, which is here below, -2/7. So I know that, you know, somehow my graph goes from here to here. And again, I don't know exactly what it looks like. Maybe it goes down and up or different things. It actually doesn't, but it could. And that's not so important to me. What is important is as I approach this, as I head from this y-intercept over to the vertical asymptote, I can go one of two ways. I can either go up or I can go down, every vertical asymptote. But in this case, I think hopefully we can see which way we have to go. Could we go up? Can you see the problem with going up? I'd have to cross the x-axis, and I know I don't cross the x-axis. So the only other option is that it goes down. Okay. Now, I can actually do some similar analysis over here. It turns out that the behavior at this x-intercept is going to work the same way that we learned with polynomials. So the x-intercept, remember, comes from the numerator, and the multiplicity of this is 1. It's just x plus 2. It's not x plus 2 squared or x plus 2 cubed, right? It's just 1. So what that means is that that x-intercept, it's going to cross right through. Right? If this were x plus 2 squared, it would come up and come back down. But this one goes right through. And therefore, since it goes through, it can't come back down because there'd have to be another x-intercept. It's trapped, and that has to be going up at that vertical asymptote. Okay. Now, we still have to figure out what's happening out here on the ends. And based on the asymptotes and the fact that there's no other x-intercepts, I have two options. Could be this, or it could be this. Right? If it's below, it has to stay below the whole time, which means it has to be going to -infinity and 0 from the bottom. If it's above, it has to stay above the whole time. There's two ways to figure this out. Probably the simplest way is to just plug in a point. So if I put in the value -4 to my function, I get minus 4 plus 2, which is minus 2. And I get 16 minus 9, which is 7. So negative 2/7 is down here. And that tells me I had to have that graph. Okay, that's a perfectly good way to do this. You will be successful with all of these. That's perfectly good. The sort of simpler or quicker option is to use what's called the multiplicity again, but for the vertical asymptotes. Okay, so x plus 3 is the factor that generates this vertical asymptote. That factor appears only once, x plus 3. It's not x plus 3 squared or x plus 3 to the 4th. It appears only once. When you have a multiplicity of 1, it's going to flip. The function is going to flip. So if one end is up, the other end will be down. Right? Multiplicity of 1. Right? Here we have the right side we knew was up, so the left side I knew was going to have to be down. Over here, right, this vertical asymptote comes from the x minus 3 factor. The x minus 3 factor is a multiplicity of 1. I know it's going down on this side. That means it's going to be coming from the top on the other side. It flips. It can't come from the bottom there because of that vertical asymptote. If that method doesn't work for you, feels confusing, you're welcome to just plot a point. Pick 4, plug it in. I'm going to get 4 plus 2, which is 6 over 16 minus 9, 6/7, right? Not surprising there. That's a positive value. That's what gives me this graph. This is the complete graph for us. This shows all of the important information. It shows the behavior at each vertical asymptote. It shows me the end behavior, the horizontal asymptote. It shows me the x-intercept, and as a little kind of bonus, it also shows me the y-intercept. So those are the features that we're looking for. What's nice is, just like polynomials, I can write these functions so that if you try and graph them using technology, you get a graph that doesn't look very good, right? It's very easy for me to see if you graphed it using technology, right? Just like the polynomials. So you got to learn how to do these by hand so that you can come up with a graph that shows these features. Okay. Questions about any of these components? I'm going to do another example for you.
So we can just pick a point and plug it into the equation?
Yes.
Okay.
It works. I mean, that strategy works when we have like the general framework of kind of what we know is going to happen. And then the point like confirms what scenario we have. Right? Like over here, you have to know enough to know kind of you only have these couple possibilities. And then the point can sort of confirm which possibility we have. If you just have a point, you know, like if I just figure out what this point is here, it doesn't really tell me anything that I didn't know already, right? It's when we have this kind of, I'm not really sure which side it's going towards, that point can help confirm that for us. Is that, it's like, yeah, it's like sometimes you just need a little extra information to help all the parts fit together. And a point can be that.
Do I always have to factor the bottom, the denominator, like you did up there?
Pretty much. I mean, we're always going to be interested in where the denominator is 0. And so to find that, we're going to want to factor it. Theoretically, you could possibly have to use the quadratic formula, but realistically, we won't give you any problems like that. You'll be able to factor anything that you would need to. Because otherwise, if you have to use the quadratic formula, you get really messy numbers for the vertical asymptotes, which is, you know, we're not quite that mean, right? We're pretty mean, but not that mean. So the short answer is yes. You'll always really want to factor both the numerator and the denominator to help you answer these questions. Other questions about this one? Okay. Let me do another one, and you'll see some similarities that will help clear some things up, I hope. Let's let f of x equal, let's try 2x squared over x squared x squared minus 4x plus 4. Okay, let's try that. So here we've got, again, a rational expression. So I think the very first steps is that when you see this kind of function, you want to imagine that you've got some vertical asymptotes somewhere in this function. Now, it may or may not look like this. There's a lot of different variations, but I know it's definitely not going to look like this, right? This is a polynomial. This is a rational function. So I'm really looking for some different things when I have a rational function like this. And as we talked about before, I want to start by factoring. I can find a lot of these features in either order. It doesn't actually matter what order I do stuff in. I always like to start with the intercepts. That's just me. So f of 0, and it turns out f of 0 equals 0 over 4, which is 0. So that's the y-intercept. And then, of course, the numerator is going to generate the x-intercept, but that's also just x equals 0. Okay. Notice, however, this x equals 0 has multiplicity 2, right? So that's a clue. You know what's happening now at that x-intercept, right? Rather than crossing through, it's going to touch it. Now, I don't know if it's coming from the top or the bottom, but it's going to touch it because it has multiplicity 2. And if you want to, it's often useful to go ahead and start to put that information onto the graph. Not that much information so far, but a little bit. So there are the intercepts. The other critical parts for us are the horizontal asymptote and the vertical asymptote. Horizontal asymptote, that's that sort of separate page I did. These have the same degree. So the horizontal asymptote is going to be 2, but remember it is a function, it's a line. So y equals 2 over 1 or 2. Okay. And then finally, the vertical asymptote, which is from the denominator. Oops, is that plus 4? Yes, plus 4. So that is x minus 2 squared. So x equals 2 is my vertical asymptote. Notice since it's squared, that's multiplicity 2 as well. So that tells me something about the behavior at that vertical asymptote. Okay. So the question is, do I have enough information to figure out what's going on with this graph? I do, but if you're feeling like you don't, you can, like we did last time, you can certainly plot a point to help you lock things into place. Okay. Now for myself, I know that eventually the graph approaches 2. Okay. And it's certainly possible for it to come from above or below, but eventually it also has to hit y equals 0. There's no way around that because that's my x-intercept. So the most simple sort of graph would be this. It wouldn't be wrong if you kind of went up and down. That's fine too. We don't know for sure. It doesn't do that, but that's a possibility and certainly fine, right? What matters is I start from here and I have to end up on this, getting closer and closer to y equals 2. Now what happens at x equals 0? We talked about that, right? That has multiplicity 2. Since it has to be coming from the top, I know that it has to bounce up, right? It can't cross anywhere else, so it has to be heading up. It has to either go up or down, but once I'm up here, I can't head back down because I'd have to cross. Now over on this side, I sort of have more information even than I need because I can just look at this side and tell you which of these spots it has to be on. It's either here or here. But you can rule out one of those directly because of the x-intercepts, right? It cannot cross this x-axis ever again because there's no other x-intercept. So there's no way it can be this bottom portion. I also knew it was going to be this top portion because of the multiplicity of the vertical asymptote. This vertical asymptote here has multiplicity 2. That means it doesn't change sign on either side. So since it's positive on this side, it's going to be positive on the other side. It's going to come from the top. Right? It was going up here, so it's coming from the top on the other side. You see the difference here for these. These had multiplicity 1, so it changed sign, right? One side was negative, then the other side has to be positive. One side's positive, then the other side has to be negative. When you have multiplicity 2 or 4 or 6, it's gonna not change signs.
So why didn't that second one go below the 2 horizontal asymptote?
Yeah, well, again, we can figure that out. So it's possible it did this. That would be okay answer as well. It's okay to cross the horizontal asymptotes. That's fine, that happens. But it's not okay to cross the x-axis anywhere else because I don't have any more x-intercepts. The horizontal asymptote just tells me that like eventually it's going to be getting close to 2. But it doesn't tell me where or from which direction it's coming towards. So I just chose this one because it's kind of the simplest version of that. It turns out that we can actually figure out if it crosses the horizontal asymptote. It crosses the horizontal asymptote if this function value ever equals 2, right? Because the horizontal asymptote is 2. Right, so it crosses it if I can find any solutions, any values that make this equal to 2. And it often looks like a bad equation to solve, but it actually turns out oftentimes to be pretty easy, because when you multiply both sides to clear the denominator, you're just going to get 2 times this, so 2x squared minus 8x plus 8. And what happens is that those often cancel. So I get at x equals 1 is the only spot that it crosses the x, that horizontal asymptote. And I can see that that is corresponding to this value right here. So that's another way of which I know that it only does this. It can't cross down. It's really the same idea as when we set this equal to 0 to find the x-intercepts. We're just saying, where does it equal 0? It doesn't have to be 0. I can pick any value I want. This is usually 0 is really nice because 0 is where it switches from positive to negative. So it's an easy and important value, but you can actually do it for any horizontal line. So I'm not positive if that comes up or not in your homework, figuring out if you cross the horizontal asymptote, but that is actually another useful thing because it provides another like kind of rails for the function, like where does it have to stay between. Does that answer your question, or does that lead to more questions?
No, that answers it.
Okay. You don't, I don't expect you to go through this work. I'm not looking for that information. So I'm very happy if you get either one of these curves.
Okay.
Say, great, full points, you hit all the important things. Okay. I'm not gonna like it if you do this, right? Because then I say, well, okay, but these are not x-intercepts, right? So that's not right. But some of the other shapes we're okay with, right? Same idea with the polynomials, right? It's like you can make it go kind of up or down a little more or a little less. I'm only focused on sort of certain parts. So with these rational, I'm focused on the vertical asymptotes, the x-intercepts, and the end behavior, and getting all of those together. Any other questions on these or this one? You know, there's nothing inherently that difficult about any of these steps that we did. Doesn't mean it's an easy problem, right? It's a hard problem because there's a lot of different parts to keep track of and sort out and put together. And I think coming up with these graphs is challenging, even if you've got all the information, right? But the right start is to make sure you can find all of this information. And that does not have to be very difficult, right? Because it's always the same. Y-intercept, x-intercept, horizontal asymptote, vertical asymptote. Okay. Vertical asymptotes come from the denominator. X-intercepts come from the numerator. Horizontal asymptotes come from comparing the top and the bottom. Okay. So those are the biggest components. And if you can find all those correctly and put all of those correctly onto a graph, even if you make some errors in the graph, If you have the rough idea of what the graph is doing at the asymptotes, you're going to get the majority of the points and you'll still do quite well. Even if it doesn't quite come out right in the end. I mean, that's our goal, right? Is to get it right. But if I don't want you to feel too discouraged if you kind of get all the parts and just are sometimes off a little bit. I think that's still a success. Okay. There's one other component I wanted to show you, which I think we have time for. So, I do want to remind you that your take-home work number 3 is due on Friday, the 9th. That's a little different. I'm trying to make sure that you get some of the work done first before you don't save it all till the very end. Okay, so that take-home is due on the 9th. The rest of our work is due as usual on Wednesday, which is the 14th, I believe. That's what I have written down. So hopefully that's correct. Yes, looks good. Okay. Okay, so let's look at this rational function. It's very similar to the other ones, right? And I do think it's actually a good strategy to go ahead and factor it in the beginning. I haven't done that with the other problems, and that hasn't been an issue, but it's possible if you don't factor in the beginning, you might miss looking at it the right way. And what we want to notice here is that unlike the other problems, there's this common factor of x plus 2, right? And you have been sort of trained that you'd like to cancel that x plus 2 out, which is a good instinct, but it does change the function. These are not exactly the same functions, because if I put in minus 2 here, I get 0 on the top, and it turns out I'll get 0 on the bottom as well. So this is undefined at minus 2. This one's not. I can certainly put in minus 2 here, and there's no problem. Okay. So this canceling has changed the function somehow. It turns out what it does is it removes what's called a hole. So this function has a hole at x equals minus 2, and this function has no hole. Otherwise, it turns out the functions are exactly the same. So you do want to work with this reduced form. This is a much easier and simpler function to work with. But I have to remember that I've eliminated a hole. So let's just see what it looks like when I come up with this graph. And we'll do this one kind of efficiently because we're getting near our time here. So notice f of 0 is going to be minus 2 over minus 3, or 2/3. And 0 equals x minus 2 means x equals 2 is the x-intercept. All right, so f of 0 is 2/3, x equal 2. So I've got my y-intercept and my x-intercept. Horizontal asymptote, these are the same, and the coefficient's 1. So it's going to be y equals 1. Right? And it turns out I can do that from here or here. The vertical asymptote is where the denominator is 0. And you may have forgotten, but what I wrote down is actually the denominator is 0 and the numerator is not 0. So it turns out -2 is not a vertical asymptote. That's tricky because you're like, well, it's -2 makes the bottom 0, but it also makes the top 0. So it turns out it's not a vertical asymptote. It's only x equals 3. So vertical asymptote at 3, horizontal asymptote at 1. And it turns out based on these 2 points and multiplicities, turns out my function has to look like that. But what I want to make sure to show is that there's this hole at -2. So the function has a hole at -2. So we draw an open circle there. Sometimes nice to label it just because it's easy to miss, or if you graph it and then want to add a hole afterwards, you can kind of make a mess of it. So just label it, indicate that's a hole. The graph is not defined there. It doesn't exist at -2. But because the numerator and the denominator are both 0, it doesn't create a vertical asymptote or anything else. It just creates a hole in the graph. Okay. Any questions about that?
Can you just repeat why there's a hole again?
Yeah, so algebraically, there's a hole at any spot, at any factor that makes the top and the bottom, any common factor between the top and the bottom. So since there was both an x plus 2 here, wherever that is 0 is going to create a hole. So like that's how you find it and write it down. The reason why it creates a hole is because the function is not defined there. I can't put 0 into this function because it makes the bottom 0. But it doesn't create a vertical asymptote because the top is doing the same thing. It turns out these two functions are identical except at -2. This function here on the right would look exactly like this, just with no hole. This function on the left looks exactly like the function on the right. It just has that extra hole.
Okay.
So, you know, there's always kind of two parts to these, like, how do I actually find the information? And then the second part is like, well, why does that information do the thing that it does? And it's really nice to know both of those. But you can certainly be successful here by just knowing how to find it as well, right? I never want to say that's enough, but if you're sort of worried, you'll be okay if you can find it, even if it's a little shaky as to why it actually does that. And we could talk more about that for sure. But it's really a numerical argument. Like as you plug in values, you can see how it doesn't blow up like it does here at 3. Anything else? Okay. Well, I will post this as always to D2L, so you can go back